All right, thank you very much for the introduction, and thank you all for being here and for the invitation to speak. So this talk will be about representation theory of Archimedean Gangros-Prasad pairs. So we'll take GH for the talk to be either a general linear group or a special orthogonal group or a unitary group differing by 1 in the index over the real or complex numbers. And we'll talk about representations that are tempered. So pi and sigma will always be tempered representations. And like many talks in this program so far, we'll be talking about the restriction of pi to h. And this is a situation where by work of many people, we know it decomposes without multiplicity. So let's just write this restriction as an integral of some sigmas with respect to some measure with some multiplicity, what I'll call m pi sigma. It's 0 or 1. And what this means concretely is we can write the inner product of, say, smooth vectors in pi in terms of this decomposition. So let's define h sigma to be 0 if the multiplicity is 0 and otherwise defined by this relation. So it's known that there's a way to normalize this relation in a way that interacts well with global period formulas. So one can normalize so that d sigma is the Plancherel measure. And so that what I called h sigma is given by an integral of matrix coefficients. So I'll write it first in an abbreviated form. We integrate over h in the group h. We choose a Haar measure once and for all for this talk. The matrix coefficient of v1 and v2 against, I'll take the conjugate of the character of sigma evaluated at the group element. And what this really means is we sum over a basis of sigma. And we, for each basis element, say k finite vectors, we take an integral. Like so. So there's a dual way you can think of what I just wrote down. I said given a vector in the tensor product of pi and pi bar, you get a number for each sigma. So we can think of this as an assignment from pi tensor pi bar to functions on the tempered dual of h. Let's say phi from h hat tempered to c. And I'll use a superscript pi to denote the ones that have multiplicity 1 rather than 0. So you send a to the function phi a, which sends sigma to h sigma of a. Okay, and you can ask the question, what is the image of this map? And now this is a formal question. So this is a direct integral decomposition. So general theorems from functional analysis tell us that this is basically a surjective map if maybe we put some adjectives like L2 and measurable. Okay. Now this is not a, well, depending upon your purpose, this might be a useful result. But we want to talk about the goal of usefully, and I'll say what I mean by that in a second, inverting this map. Useful, of course, depends upon what you want to do, what your use would be. But maybe just a teaser. The functional analytic argument I gave gives you no idea how g acts on the vector you produce in pi tensor pi that gives rise to a specific function on the dual of h. So, e.g., we want to show the g action. Oh, I forgot to mention, this is joint work with, actually, Venkatesh. Yeah, I guess I got carried away. So let me, I'll write that when I erase. So this is a local problem that I'll describe more precisely and state some results towards a bit later. It's motivated by a global application, which I'll indicate briefly now. So motivation. Let's just start with the simplest case. So let's take, say, GLN. And let's assume that pi and sigma arise as cusp forms. So to set that up, let's take gamma h to be the same thing with z. And let's let pi be in L2 cusp. I won't write it, but I'll assume it's a Hecke space as well. And sigma in L2 cusp of h mod gamma h. And let's take some vectors v in pi and u in sigma. So then there's the theory of Hecke integrals for GLN plus 1 GLN due to Jacquet, Pititsky, Shapiro, and Shaleika, which tells us that if you integrate, say, v times, let's say, the conjugate of u over the quotient of h, you get an L function, Rankin-Selberg pi tensor sigma conjugate, times, let's just say, it'll be an integral of Whittaker functions, but let's just say a local integral at infinity that depends upon the vectors v and u. Okay. We can square this identity out and say sum over a basis of the representation on the smaller group, sigma. And if one normalizes this by the adjoint L function at 1, so then this factor here arises from it's simplest just to say it's the adjoint of pi at 1 times the adjoint of sigma at 1. Yeah. This is something that appeared in one of Wei Zhang's papers. That one can write this square of this Whittaker period in this way. And so I'll state a theorem in a bit of an informal way. So this is the motivation for the talk. Although the talk will be about the local problem I advertised. So let's not consider what I just wrote above, but let's consider the SO or unitary analog. So this is the subject of Achino Ikeda, conjectures, Neil Harris, and the theorems of Wei Zhang, and perhaps others by now. Let's assume some local conditions that I won't write down in full, but I'll give the most important ones. So say compact quotient, and let's take all our groups to be quasi-split at infinity. Infinity will be like some real place of the number field in general. Let's fix pi as above, as throughout the whole talk. Let's take a parameter t going to infinity, and let's consider the following family of forms on the smaller group. I'll call it ft It'll consist of all the sigma with the property that they have, let's say informally speaking, fixed level. Assume they're distinguished by pi at the place that I've called infinity. And I'll assume that they live in some rescaled ball as quantified by their infinitesimal parameter. So omega will be some nice compact set, measure zero boundary, avoiding the origin. And we rescale it and we ask that the infinitesimal character live in it. Okay. And as advertised at the beginning, everything here will be tempered at the place of interest. Okay, so then the conclusion is the following. Let's introduce some shorthand. I'll call this script L of pi sigma. So it's a square of an L value in the general linear case, and in the orthogonal and unitary cases, it'll be an L value itself. And the theorem says that the average of these L values tends to the number 2 as t goes to infinity.
So your L values are the way I would like finite. In other words...
Yeah, no Archimedean. Is that...
Yeah,
sorry.
Because if you put in the Archimedean fact, then you vary over this kind of family, then you've got these exponential...
Right.
The average is not going to be 2.
Yeah. So
L means probably the finite. Right?
yeah, exactly. So
Okay.
this is the good normalization.
The audience here for L includes the Archimedean phase.
Ah, okay. So let me, yeah. Thank you for cautioning that L is the finite L factor. Yeah. All right. So how are we doing? Is it okay? All right. So what was I going to say? Yeah, all right. So I won't talk too much about. Well, I mean, the whole talk will be motivated by this, but let's just break down the basic strategy, which is.
You're not going to explain number 2?
Nope, not today. But sorry. I know it's enticing, yeah. All right, strategy. Let's note the following identity. So this is a strategy that isn't like new to this paper. It's been employed by many people. I think most systematically first by Bernstein and Reznikov in this sort of setup. So if we take the identity I wrote up here and we sum it, as I forgot to do, not only over U in a basis of sigma, but let's say over all sigma, then we get basically a Plancherel decomposition on the quotient H of H. So we have this sort of identity without any restriction. Yeah, I mean, we can impose crazy conditions at other places, right? Yeah, like we'll have like we'll have a number field like with at least yeah. So I'm trying to yeah. Just infinity is one place of a number field. I mean, I didn't want to get into the actual formulation, so.
I take it the global sign is better because +1 somehow constantly in the family.
Yeah, it is. Yeah, that's right. Yeah. Yeah, thanks. Okay, so the strategy is the following. Suffices to find, say, a vector v in pi such that a few things hold. So, all right, one of them here. One, we'd ask that this H sigma pick out the family. Should be roughly 1 if we're in the family and 0 if we're not. Two, we should show that the things that I didn't write here So like the non-cuspidal contribution is small. And 3, we should show that this integral converges to twice the size of the family. Or let's say is asymptotic to twice the size of the family. So today I'm going to talk about step 1, which will be a local question that I think is of independent interest, and it relates to actually most of the talks we've had so far in this conference. So, well, I mean, not only that it involves a restriction problem and kind of a rescaling of characters, but we had, these talks on, say, construction of supercuspidal representations yesterday, and we'll use techniques that are kind of in the spirit of some of Howe's early work in that subject. So that'll be the plan. And some of the ideas will also be related to implementing 2 and 3.
What is number 2? What is the brackets?
Number 2 is to show that the non-cuspidal contribution is small. Yeah. Okay. So one preliminary observation is that we can generalize the strategy I've written on the right a bit right away by working with families of vectors. Number 1 says that H sigma of V tensor V, maybe with a bar, is the, this is notation for characteristic function of the family. Let me write it big here. So 1 says that H sigma of the vector in pi should be roughly 1 if sigma is an FT and 0 otherwise. Is that? Well, it suffices to find a vector. It suffices to find any vector. I'm not.
He wants the vector to do the counting.
It'll make some sense. So let's just generalize it a little bit, though. It really suffices to find an element of pi tensor pi bar with the property that this identity holds true.
Should I think of suffice to find the test function really with the relative character?
Yeah, we'll pull it back to that in like 1 minute.
Can you remind me again what is this H sigma? You hold it so large now.
I'm going to rewrite it again in a second. So, hold on, guys. I got. Yeah. Yeah. All right. So let's just recall some things. So let's recall that pi tensor pi bar can be identified. Let's say Hilbert-Schmidt tensor completion of both sides by identifying AV tensor V summed over a basis with an operator A. Okay, and in this optic, which is the one that I'll assume for the rest of the talk, to answer your question, the relative character is given by the integral over H and H of the trace of pi of HA times the conjugate of the character of sigma. Okay. And a good example of operators are convolution operators coming from the group. I hope that's readable. So f is in CC infinity of G, and we're going to construct an operator using a function. Now the functions we're going to use will be supported close to the identity. So it's natural to pull this back to the Lie algebra. And both the tools we'll use to analyze them and the results that we'll get will be expressed on the Fourier side. So it's convenient to pull this back to the Fourier dual of the Lie algebra. So let's write G for the Lie algebra. Let's write G hat for the Pontry eigendual. So we have X here, Xi here. We'll have a pairing between them that gives some imaginary number. We'll have a Fourier duality between functions on both sides. And for a function a, let's say a Schwartz function on g hat, let's define an operator in the only way we can by integrating the Fourier transform onto the Lie algebra of the group against the representation pulled back under the exponential map. And so the structure of the rest of this talk will be I'll state a theorem describing what H sigma of op A looks like for certain classes of A. I'll kind of indicate the proof, and it'll be clear throughout the course of that why this actually produces vectors that are useful for the goal that we started with. So a bit more precisely, so we'll consider, we have this parameter t that goes to infinity that indexes our family. So we'll consider A depending upon t satisfying some uniformity as t goes to infinity. And I'll single out an example. And I'll call it example 1. So you can take A of xi to be, say, A1 of xi divided by t, with A1 a fixed, say, compactly supported function. On the dual of the Lie algebra. And finally, just to be completely honest, we're actually going to just restrict to a fixed neighborhood of the identity here. This will be fixed, and it'll be identically 1 near the origin. And this will have little effect on our applications because with this rescaling, the Fourier transforms we get will be concentrated within about t inverse of the origin. And that's the actual definition we work with. So about the only things we can do with these operators to start are we can say, like, try composing them. More on that later. Or we can say take their traces. And so this will be the main input. So the Kirillov formula, so the character formula in the form of Kirillov tells us what these look like. So the trace of op A. He gives an exact formula, which I'll write. So chi and A check are what I wrote above. Here J is Jacobian of exponential map, normalized to take the value 1 at the origin. And I guess all that really matters for us is that, I mean, we can think of this as basically an integral over O pi of A. We're here, so the content of the theorem is there exists a coadjoint orbit and there's a natural measure on these. It's the canonical symplectic measure. And this identity here we can think of as, say, holding basically lying just a little bit in cases when A is, say, 0 for the case of example 1. So morally, the formula says we can think of the character as being given by this integral over some orbit in the dual. I mean, experts might know I'm lying a little bit in that you can have a finite union of orbits sometimes and things like that. OK, and let's take a moment to look again at what H sigma of A was. Let's try to understand heuristically what we should expect this to be asymptotic to. So I'm going to erase it and then rewrite it. Again. So these are heuristics. So h sigma of op A is equal to the integral from before, and I'll write out the definition of op A, and I'll take the trace. I've ignored the truncation chi, and I'll put a dot here to note that I've lied a little bit. Let's do the following. Let's pretend that the exponential map were an isomorphism. And if that were the case, we could write the integral over h as an integral over the Lie algebra of h. And that'll give us the following kind of integral. Say of h of x, chi pi of e to the y, e to the x, chi sigma of e to the y bar, let's call that e to the negative y. And again, continuing with the heuristic that we pretend exp is an isomorphism, this is given by e to the y plus x. And so we might recognize, if we try to express this back in terms of A, that we're taking a convolution on this side. We know what the Fourier transform of the characters are. It's given by the above formula. So on the other side, it should be expressed as a product of their Fourier transforms. So I'll write what we get by that heuristic. So we might expect this to be given by an integral over O pi intersect the preimage of O sigma of the function A we started with. Because again, O pi is kind of the Fourier transform of chi pi. O sigma is that of chi sigma, and we're convolving. So we might take the product, which amounts to integrating over the intersection. And I'll refer to this many times, so I'll call this O pi of sigma. So the natural question, if you haven't looked at these things before, is what does this set O pi of sigma look like in practice? So let's give an example. We'll call it example 2 just to refer to it later. So let's take G to be, say, PGL2R. Is there a question? Or? Yeah.
Before you explain what O pi
Yeah.
of sigma is, can you remind us what O pi itself was?
Yeah, O pi was the basically Fourier transform of the character. So it arose in this formula. And maybe, I mean, this is integral h of x with chi pi of e to the x by definition. So again, it's just a heuristic at this point, but it'll lead us to some idea of the answer. Let's consider pi, and let's take pi to be a principal series. Let's take sigma to be a character. Let's call their parameters t and t prime. Now let's draw a picture of what O sigma looks like, or O pi sigma. So here we can identify the dual of the Lie algebra with with R3, say taking coordinates x, y, z, like so. And we can map that to h hat, which we identify with R. And then in this in these coordinates, O pi is given by this equation. And O sigma is given by just a singleton. So the picture looks roughly like the following. Yeah, all right. So this is the projection onto h hat, the real line, given by sending x, y, z to just the x coordinate. And this point and this point project down to the points negative t and positive t. And so what I called O pi sigma will be cut out inside this by the equation x equal t prime. Let's draw what the solution to that system of equations looks like here. Let's take, for example, t prime to be this point, just a little bit to the right of the point t. So the solution looks like a family of, or it just looks like a hyperbola. So it'll be an orbit under the action of h. Maybe I didn't draw it boldly enough, but it's kind of a very nice set. On the other hand, if we take t prime to be something like negative t or positive t, we get a slightly different looking set. So we'll get a set that intersects this point here. And so we'll note that in the two examples, there's a dichotomy. So here there are two h orbits, one given by the axis minus the origin, the other given by the origin. Whereas in here, there's a single h orbit. H will act transitively, even simply transitively, on such points. So the points that live over here, let's call this xi. And let's call these ones, say, xi prime and xi double prime. We're going to prove an asymptotic formula for symbols supported near these good points that don't have weird behavior. So let me say what I mean by that now. So the point xi is stable in the sense of geometric invariant theory under the action of h. So this says it has finite, in this case, actually trivial stabilizer and a closed orbit. So xi prime and xi double prime are not stable in the above picture. In the case of xi prime, because it has a non-trivial stabilizer, and in the other case, because it has a non-closed orbit. The closure of the orbit contains xi prime. Okay. So we check, by the way, that one can rewrite this in the case that xi belongs to O pi sigma in a purely analytic form by saying there's no conductor drop. And I'll put that in quotes because I don't want to explain it in detail, for the L function L pi times sigma 1/2. So in this example, you can, I mean, if you're familiar with analytic conductors and L functions and subconvexity, you'll know that it's exactly when the parameter t prime equals either t or negative t that you have a drop in the conductor. And so that's a general feature characterizing this analytic phenomenon of conductor dropping in terms of a geometric invariant theory phenomenon. So with all this set up in this definition, we can state the main theorem that I wanted to. So let's fix omega in G hat to be a nice compact collection of stable elements. So elements away from the bad line that I drew over there, or the corresponding one on the right-hand side. Let's fix a number rho strictly greater than a half and up to 1. And let's let A be an element of CC infinity of the rescaling of omega with the property that we have some control on its alpha partial derivatives for all alpha. So we'll ask that this be bounded by a constant depending upon alpha times t to the negative rho alpha. Just to give an example before I state the theorem, this condition is implied in the basic rescaled case of example 1. And we can take rho equal to 1 in that case. So taking rho smaller makes the problem more difficult. Taking rho equal to 1 is sort of the easiest version. But we'll need the general case actually to prove even the rho equal 1 case. So OK, with all that set up, maybe I'll keep the picture for now. Let's state the result. So then H sigma of op A is equal to the heuristic thing that we said we should expect plus an error of order 1 over t to the rho. And when I say integrate over here, so this in the examples, in the stable cases, will always be an H torsor. And so we can transport the har on H to it. And that defines a measure. We also needed to make such a choice in the definition of this so everything's consistent. So that's the statement of the theorem and what I wanted to explain a few things about the proof today. So there's a remark to there are a couple of remarks to make. So one, the theorem quite strongly solves the motivating problem, because if you have a function on, say, h hat supported away from t and t prime, like let's say a function maybe supported here given by a little bump, it's a trivial geometric exercise to produce a function, say a, on the orbit opie, whose integrals over these h torsors give you the function down here. So this solves in a very strong form the, yeah.
Can you remind
Yeah, sure.
what this proves, what the application is?
OK, so let's note in this example, for all k in, say, R take away plus or minus t, we can find a set omega as in the theorem. So I mean, think of k as being this bump. Think of this blob maybe being omega. And there also exists an a as in the theorem, supported in omega, such that the integral over opie sigma of a is equal to k of, I guess, the parameter t prime. So this is in example on the top board. Does that make sense? OK. And I mean, I've stated it in a weak form, but of course, if we have some regularity on k, we can easily get regularity on a. I mean, it's a principal fiber bundle with fiber h. We're zooming in locally at a point. OK. So I wanted to make another remark about the relation of this to say, germ expansions. So I mean, we saw in Professor Walsperze's talk yesterday the statement of the Harashandra germ expansion of a character of a group G. And so the more exact form of that is, say, the Kirillov formula or any exact Kirillov formula when it's available. So it's in these formulas that you see general orbits rather than just nilpotent orbits that you get by rescaling. And so there are many papers where people study relative characters roughly in the spirit of what we define here. And so theorem 1 roughly fits in as an analog of the Kirillov formula in the relative case, where you're not rescaling, but instead working with a varying collection of representations, pi and sigma. So I hope for those of you that have thought about these things, this clarifies the relationship. So to emphasize that point, all right, we allow pi sigma to vary with t.
So I see you're using non-unipotent orbits in the Kirillov formula and your formula.
Yeah, so I mean, the orbits might look like this, which are non-unipotent. Yeah. Okay. All right, I think that's all I wanted to say about the result, and now I'll say some things about the proof and also the ideas and the methods that go in both this result and the
Can you do more than just invert kind of a bump function?
You're asking, have we thought about uniformity for like a...
If you want to put in more harmonics there. I mean, there should be some kind of full inversion formula. It seems like you, in your application anyway, you're just taking the set of stable guides and then expanding it, which is a very simple function to create
Right.
on the transform to be 1, basically, so that it doesn't decay.
Right.
You might be able to do much more in this inversion process. Huh?
Yeah, we can get, I mean, we can get any bump function, say, but what kind of more generality are you thinking?
If you were in, what's an example that you were doing in GL2 and geodesic,
Mm-hmm.
maybe state. But you sometimes might want to amplify or put in some phases.
Ah, okay. Yeah. So I mean, we can allow k to be irregular by using this parameter rho, for example. We can have it concentrate somewhat. I mean, that'll be the last sentence of the talk, if I get there. But all right, let's say something about how we can do this. All right, so the first thing we're going to do is the other thing I said we could do with the operators. Yeah.
So you pointed out this formula holds for stable orbit, which means O pi sigma should be away from
Yeah.
bad points. But what's the definition for this?
I mean, we haven't defined a measure there for general ones here. Yeah. So even the definition of the right-hand side depends upon the hypotheses of the theorem.
You should be able to tell us where the 2's coming.
All right, I gotta say. Well, let me try to say some other things. So I can give another talk if you want, but all right. So we work on a calculus for Ape, which we remember was this integral. It involved a chi of x, which I'll ignore for the purpose of exposition, over the Lie algebra G. And of course, the first thing you can ask is, can you compose these things? Okay, and the answer you'll kind of check by some elementary calculus is yes, you can compose them, ignoring the chi for now. And the composition is given by op of something else, where that something else sends a dual Lie algebra element zeta to some integral. This will be an imaginary number in the exponent, and here x star y is logarithm of x exp of y. All right, so we'll work out a calculus for these things. So I'll just state a proposition, which says, so A star B, if it's an asymptotic expansion that I'll write like this, where star J will be some finite order polynomial coefficient differential operator. Just to give an example, at the 0 level, it's just given by the product of the two functions. And it's given by basically taking a Taylor expansion of this function minus the linear part that comes from its leading asymptotics. Okay. And the precise meaning of this is the following. So precisely, so we can set, say, S m rho to be the set of all functions on G hat. I'll let them depend upon the parameter t with the property that their derivatives satisfy some bounds. So then star defines a continuous map between these spaces where you have to add the upper indices. And the interpretation of these remainders is that these will belong in kind of smaller spaces. So you'll gain some powers of t inverse. When you apply these operators, so this will converge in a reasonable space of functions. So if you've studied the pseudo-differential calculus, you'll recognize this as kind of an exact parallel. And in fact, if you take G to be a Heisenberg group, this is quite literally that story. So the next thing we do is we show that op extends in a reasonable way to these classes and gives a reasonable class of operators that I'll call psi m, which we'll define to be the space of operators, say, on the space of smooth vectors in pi that satisfy some nice properties. So we'll ask that for all integers R and S, and I'll just write it down to show that it's something kind of explicit and convenient. So for all, say, elements in some basis of Lie algebra, we'll control operator norms of iterated commutators of these elements, where the operator norm is as an operator from some spaces pi s to pi s minus m, where pi s is defined by the s power of some elliptic operator on the Lie algebra of the group, given by a sum of squares plus 1, say. And this inclusion is continuous, and it satisfies other nice properties, like these norms on the space of operators on pi that we get from what I wrote here turn out to be useful to control just about everything one would want, like trace norms and things like that. Okay. So this allows us to implement a technique that one might call micro-localization. I mean, I should say, by the way, I mean, philosophically, this is all kind of what people do all the time in pseudo-differential calculus. So I guess our contribution here is to read Hormander and figure out how to make the right definition that works here.
Let's be clear
But
about one thing.
yeah.
For the gross percent type formula, you need the symmetric, you need those kind of examples you wrote down. Where exactly are you using in this pseudo-differential calculus? You've got G and H. And does H have to be one of those examples, or is this part of a more general theory?
So this is a rather general calculus, let's say, for reductive Lie groups.
But what property does H have to satisfy in order for you to calculate?
So G and H, I mean, we do a lot of kind of algebraic geometry involving G and H just to figure out where the stable locus is and things like that. But otherwise, we just use the character formula.
But what the theorem, and that applies
Yeah. That applies to all reductive groups, all nilpotent groups.
I'm asking what wrong with H.
So the calculus is right now just about G.
Okay.
And I'll say in a second how we actually use it with both of them. But I mean roughly we'll, yeah,
So far,
great. And it's still going to be G for just a second. I mean, I just want to say what the philosophy is and how it relates to Howe's theory real quick. So let's let omega be an element of G hat, maybe of size roughly t, the scaling parameter we've used for the whole talk. Now let's consider a omega to be some smooth bump near omega, maybe within a distance t to the rho. So something like this. Say for phi fixed. So let's consider the operators these define. So the output of our calculus is roughly that you can think of these p omegas as a system of independent idempotents, which will have rank basically 1 if you take a rho to be close enough to a half. So morally, they describe a basis for the representation. And so I mean, nowhere in all this are we using an explicit model for the representation. I mean, we could be working with discrete series representations for which we don't know how to construct a model very easily. So here's the moral. The set of all p omega, where omega goes over, say, the coadjoint orbit, and let's say it's t rho spaced, is roughly the same as a complete system of independent idempotents. And one can compute their rank using the Kirillov formula. It ends up being t to the demo times roughly rho to the 1/2, which you can think of as basically being 1 if rho is about 1/2. So we have something here that's basically as good as a basis for the representation for many purposes. And and this comes back to my promise of relating this to the supercuspidal talks, in that if you take R instead to be a p-adic field, and you take rho to equal 1/2, this is basically what what Howe's early papers is doing. And I mean, what I said becomes a literal truth rather than an approximate truth. I'll give one example of how this philosophy can be used to estimate something. So let's prove like. So let's take omega to be moreover stable. And so now I'm going to introduce the group H. Let's take H to be an element of the group H, which is like kind of big. So let's take it to be of size t to the -1 plus rho plus epsilon. Yeah.
The period formula requires the H to have G and H to be a pair of a certain type. This calculus, at this point,
Right.
Are you just going to make dumb functions in asymptotics, or so what is it on H you're really using at this point?
So I mean, really, we just use the fact that we have these stable loci for the action of H on the Lie algebra of G.
So it could be more general.
So yeah, it could certainly be more general, but we've only proved that these things exist in the examples we have here. So, and I mean, we really use that we have a strong Gelfand pair, and I think maybe those are not so far off from the class of.
So where are you using that in this?
Well, just to set up the multiplicity. Oh, okay, not in the calculus. Yeah.
In your special calculus?
Nowhere. I mean, it's very, very general. Yeah. So the lemma I wanted to say is, under this condition, the trace of the translate of p omega by h is very, very small, like of size t to the negative infinity. Let's just think about this for a second. I mean, I said here we can think of these as a complete system of independent idempotence of rank roughly 1. So we can think of p omega as being roughly maybe v omega tensor v omega bar for some unit vector v omega that transforms in a simple way under elements within about distance t to the negative rho of the identity. Okay? So the proof, just in kind of word form, is that this thing here will be roughly the inner product of v omega with its translate by h. But h dot v omega will be up to some sign maybe v dot h omega, because everything in sight is equivariant. And the stability condition implies that the distance between h omega and omega is bounded by, well, this number I wrote up here times the size of omega, which is now bigger than t to the rho plus epsilon. But these things are concentrated at scale t to the rho. So what I wrote implies that their supports will be disjoint. And so this calculus that I wrote earlier gives that they have major decay. And finally, I'll conclude my talk by just saying something about the proof of theorem 1. And I think since I'm out of time, I'll just say it in a couple words. So the X heuristic works for h minus 1 small, say about size t to the negative half. And then otherwise, you can just apply the lemma to deal with the larger values of h. And it becomes a kind of pleasant exercise in working with this calculus to prove this. I don't know of a way to actually do this calculation in the generality we've done without using these things. And I promised you that I'd make the last sentence of the talk be, hey, what happens in the non-stable case? We've checked it in this one example of GL2 to GL1. It gives a kind of interesting answer, but I think I'm out of time, so teaser.